Welcome to this video. We've learned about phase difference, and now we'll take some notes to make sure we've got it down. When graphs start at different places, they have what we call a phase shift, which is a fancy way of stating phase shift, and the variable we use is the Greek letter phi. And this is a fancy way of just saying they start at different parts in the cycle. Now we can think of phase shift in terms of percentages. So for example, if the graphs look like this, then that is a 50% phase shift. Or what we would really say is, instead of 50% of a cycle, we say pi radians, which is half of 2 pi. The total amount is 2 pi. If instead they're off by only a quarter of a cycle like this, then the phase shift would be 25%. Or a quarter of one full cycle would be 2 pi over 4, which is pi over 2 radians. Now, there's a formula we can use to calculate this when we're dealing with time graphs. See these time graphs? The formula is the phase shift. You take this 2 pi radian, and only some fraction of it is the phase shift. The fraction is the difference in time between the two graphs divided by the time for one full cycle. So the delta t over big T gives us the fraction of a cycle that the graphs are off by. When we take that fraction and multiply by 2 pi radian, now we have what fraction of 2 pi separates the two graphs. So this is a very visual thing. Let's take this example. Okay, how far off are these two graphs? That's the phase shift, right? Well, how do we figure it out? See how they don't start at the same spot? What you do is you find a nice distinct spot on the first graph. I'll take this peak here, and you trace it down, and you find the exact same part of the cycle on the bottom graph. So this is the second peak, right? So 1, 2, here's that same spot on the second graph. And clearly there is a difference in where those two are located. The second graph is farther to the right, shifted to the right. So what's the amount of that shift? What is the phase shift? They ask us to calculate in seconds, radians, and degrees. So first, we look at seconds. What is this interval of time right here, just in pure seconds? Well, the first line is at 2 seconds. This line is, let's see, this is 2.2, 4, 6, 8, and then 3. So this one is between 2.2 and 2.4. Let's just call it, this first is 2.0 seconds, and this one we'll call it just 2.3, since it's between the two, between 2.2 and 2.4. So the difference between them, this little sliver, delta t, from one to the other, is 0.3 seconds. Now if we wanted to calculate the fraction, well, we're going to do that. Now let's calculate in radians, because that's really what the phase shift is. So here, whoops. Here I use my formula. I take the delta t and I convert it to a fraction of one cycle. How do I do it? By dividing by the period, the time for one cycle. And then I multiply by 2 pi radians. Okay. So the delta t was 0.3. And is that big or small? Well, the way I figure out if 0.3 is big or small, I compare it to the time for one cycle. Here's the time for one cycle. We go down, and then back up, and bam, we're done. So a cycle ends after 2 seconds. That's the period. And then we multiply by 2 pi to convert this fraction, this portion, or percentage, into radians. And what do we get? This is 0.94 radians. And we can convert that also to degrees finally. So this is part A. The time difference is 3.3 seconds, part B. And then part C, we convert this into degrees. So we know that we've got 0.94 radians. I'm converting, so I have to set up a conversion factor. I want to cancel out the radians, and I want to convert it to degrees. So 1 cycle is 2 pi radians, and 1 cycle is also 360 degrees, so those are equal. And when I calculate this over 2 pi and times 360, I get 54 degrees. Okay. The final thing for us to learn is in phase and antiphase. So if we have a cycle where the two oscillating systems are always at the exact same spot, right? So they're both here, and then they're both at equilibrium. Here's the second one below. And then they're both at maximum displacement. And they're always at the exact same spot no matter where they are in the cycle. They match. Here's equilibrium. That we call in phase. And they're easy to spot graphically because the graphs look like this. Whether it's the velocity graph or anything else, the point is that the graphs are identical. Wherever one starts, the other starts at the same spot. And so these are the displacement time graphs for the two systems. Now, another way to say this, and in phase means that the phase shift is 0. 0 degrees or 0 radians. By contrast, out of phase. What's out of phase? Well, if you have systems that are always exactly at opposite spots, or stages. So when one of the springs is at the far left edge, the other is at the far right edge. They're both at equilibrium at the same time, but they're moving in exact opposite directions. The top one is moving to the right, and so it stretches out next. The bottom one is moving to the left, and so it scrunches up next. So they're always at exact opposite parts of the cycle. This is called out of phase, or antiphase is the word we use, the British term that we use in IB, antiphase. And it means the phase shift is 180 degrees, half a cycle, or pi radian. And what do the two systems' graphs look like? Here's the first system, position time, and here's the second system, position time. It doesn't really matter where the first one starts. The point is that let's make it a negative cosine curve. Why not? The point is this one is exactly 180 degrees. It's a mirror image, or it's as though if we continue this graph, right? And we continue this graph. Instead of the bottom graph starts here, the top graph starts here. And so how much is that? That is half a cycle, because this would be full cycle. So half a cycle is 180 degrees, it's pi radian, yeah. Okay, and that's phase.